Hi, welcome to Chapter 5. All of Chapter 5 is about area, and we're starting with 5.1, which is 5.1a, which we're going to discuss area and perimeter in 5.1a. These are some of the questions we hope to answer in 5.1a. Does area depend on perimeter? Does perimeter depend on area? How can you find the largest area for a given perimeter? And do the lengths of the sides of a figure have to be integers? So let's go back to some of the formulas we know for finding area. With a rectangle, we can think of it as length times width, or also base times height, calling this the base and this the height. For a square, we know that all four sides are the same, so we could just call each side s and do s squared, or you can always go back and use your regular formulas, base times height for a square. For a triangle, you're going to need to know the altitude of that triangle, or the height of the triangle, and then the base. And then the area is 1/2 base times height. You can also think of that same formula as base times height divided by 2. So, just with that amount of information, we can fill these in. A square with side length of 4, we want to find the area, and we want to use the correct units. Whenever we're finding area, it's going to be units squared. So this one is in centimeters. Each side is 4 centimeters, so the area equals 4 squared, which equals 16 centimeters squared. A rectangle with width of 5.2 and length of 5.8. So I'm going to let you go ahead and do these. This is going to be base times height, which is the same as length times width, since they're referring to it as length times width. You're going to go ahead and multiply those and make sure your answer is units squared. I'll come back with the answers in a minute. For number 3, a triangle with the base length of 11, so 1/2 times 11 times 6.5. So without a calculator, I'm just going to do this. I'm going to do it as 1/2. I forgot I can't erase on this. So I'm going to do it as 1/2 times 11 over 1, and 6.5 is 13 halves. And then I'm going to just do cross canceling. Well, actually I'm not. Can't do any cross canceling here. So I'm going to let you go ahead and find your answer to that and make sure you know it's going to be centimeters squared. And we'll come back and show the answers at the end of the slide. For the next one, and you can put it on pause and go ahead and do those problems. For the next figure, I'm going to have to divide this figure up into different shapes. I can do the triangle on top, and then I can do, there's a couple of ways you can do this odd-shaped figure. I would be, first of all, we can separate it into different ways to do the figure on the bottom. I'll go ahead and do the area for the triangle on top. We're just going to have 1/2 times the base is 10 times the height is 12. So that would be 5 times 12. We have 60 centimeters squared for the triangle on top. Now for this other figure, I would be tempted, I want to find out what these lengths are here first. So I know that the whole thing all the way across is 10, and in here is 3, and I've got 6 left over, and dividing it equally because these two are congruent. So that means each of these are going to be 3.5. So there's a couple of ways to do it. I guess I'm going to separate it into 2 figures. I'll do 2 different rectangles, which means we didn't even really need to find that measurement if you're going to do it this way. So the bigger rectangle is just base times height, which is 10 times 4 equals 40 centimeters squared. The smaller rectangle is just 3 times 3, base times height, 3 times 3, which is 9 centimeters squared. We just have to add these together, so the total is 109 centimeters squared. Didn't really even need these if you're going to do it this way, and you've already got the area. Okay, going to number 5, what does the area of a figure measure? It measures, of course, the space inside of the figure, and the perimeter is the length around the figure, the length all the way around the figure. Okay, number 6, if you owned a piece of farmland, why would you want to know its area? So if you owned farmland and say you were growing crops in the farmland, then you'd need to know how much area there is to know how much to plant. And knowing the area will give you an idea of what kind of produce you'll be able to plant and how much. Why would you need to know perimeter? Well, say you had livestock, like cattle, that you wanted to keep within a region of your farmland. You might have to put up a fence all the way around it, and the fence would be the perimeter to know how much fencing that you're going to need. On page 322, it has some of these definitions. First of all, polygon, if you can follow along in your book, but it is a many-sided plane figure whose sides are line segments. So you can put this on pause, look at page 322, it's the last sentence there. A many-sided plane figure whose sides are line segments. And then right after that, it talks about a polygonal region. It consists of a polygon and its interior. That's just a polygonal region. And then it goes on to the next page to say a polygonal region can always be divided into non-overlapping triangular regions. Then the book, following right along in the book, it goes into the area postulates. For every polygonal region, there is a unique positive number called the area of the region. This is the same area postulate, if two polygonal regions are congruent, then they have equal areas. Remember that a perimeter and area measure different things. Perimeter is a distance, it's a distance or a length. So it is measured in linear units, for example, inches and centimeters. Area is measured in square units, square feet, square meters. Area addition postulate, the next postulate, right, still on the top of page 323. The area of a polygonal region is the sum of the areas of its non-overlapping parts. So we already did that in the warm-up exercise, but now we're going to do it in this figure. We can divide this figure up into 3 different figures. We've got a triangle, we've got a rectangle, and another triangle. So finding the area of that figure, we could do the triangle, 1/2 the base times the height. Oops, the height is 5. So 1/2 of 15. The first one is 7.5. The other triangle, number 3, is also going to be 7.5. And then the rectangle is just base times height, 6 times 5, or 30. So that's 15 plus 30, 45. And since we're finding area, it's going to be inches squared. Okay, for number 2, we are being asked to find the it's asking us if we can make any conclusions about the sides of this quadrilateral. So in order to make conclusions, I'm going to examine all the different little triangles. This triangle and the one below it, are they congruent triangles? So I see that we have side and angle and side. that are the same. So by side, angle, side, those two are congruent. And the same thing's going to be true on the other side, that we also have side, angle, side. So yes, they're congruent triangles, which tells me this angle, this segment is going to be congruent to this one, and this segment congruent to this one. Let me just erase my other marks. So can you make any conclusions about the sides of this quadrilateral? Yes, these two sides on the right are the same, and the two sides on the left are the same. We can prove that from doing congruent triangles. I'm going to hold off on this definition for now. This is going to be something that we call a kite, which we're going to come across a little bit later. Instead, I'm going to go on to number 3, which says the dimensions of a rectangle of area 72 are whole numbers, no fractions or decimals. List all the dimensions of all such rectangles. So thinking about it, I'm going to list them all in here. Like the first one can be 1 times 72. So it's a really long, thin rectangle where the side is 1 and the height is 1 and the length is 72. Or the length is 72 and the width is 1. And then we've got 2 times 36, so the width being 2, the length being 36. We could have 3 times 24. We could have 4 times 18. Not 5, but we could have 6 times 12. And finally 8 times 9. And then they would start to repeat. So it wants to know if one of these rectangles is chosen at random, what is the probability that it has a perimeter greater than 40? So we need to figure out the perimeter, which we'll do with the equation 2L plus 2W. So in the first example, I've got 2 times 1 plus 2 times 72. That's going to end up with 144 plus 2, or 146 as the perimeter. So you see there's going to be a huge difference in these perimeters. And it will follow a pattern. The next one, which will be a little wider and a little shorter, the side is 2. So 2 times 2 plus 2 times 36, which is going to be 76 plus 4. 72 plus 4, which is 76. The next one, so the perimeter has gone down quite a bit, just changing that shape. Next one again, it gets a little wider and the length shortens. So 2 times 3 plus 2 times 24, 48 plus 6, this one is 54. All of these right now are greater than 40. The fourth one, 2 times 4 plus 2 times 18, I think that's 36 plus 8, which would be 44. Still over 40. Now the shape is changing, 6 by 12. It's starting to approach a square, and this is going to be as close as it's going to come to a square. So we've got 2 times 6 plus 2 times 12. That would be 24 plus 12, or 36. So finally, this one is below 40. And the last one, 2 times 8 plus 2 times 9, 18 plus 16 is going to be 34. So these first 4 out of a total of 6 are going to be greater than 40. So it would be 0.67, rounded off to 0.67, or 0.6 repeating, or a 66.7% chance of the rectangles being greater than, having a perimeter greater than 40. Going on to number 4. It says the area of rectangle RCTN is 6 times the area of rectangle AECT. The first one is RCTN, so that would be the biggest rectangle, and 6 times greater than this one on the right. And then it gives us coordinates as if it was on the coordinate plane. Find the coordinates of A. So the length of this whole thing is -12, so the length of NT is going to be -12, or 12 units, plus 24 units. So 36 units. And the height of the whole thing is 8. So the big rectangle, RCTN, is 36 times 8, which is 288. And it says that 288 is 6 times the area of the smaller rectangle. And we know the smaller rectangle has one dimension is 8, and the other one is an unknown. And from that, we're going to figure out what the unknown is. 288 equals 48. N, dividing both sides by 48, we get that unknown length is 6. And now we want to find the coordinates of A. So we just figured out this right here is 6. The whole thing over is 24. So the length from the y-axis to A is going to be 24 minus 6, or 18. So it's over 18 and up 8. I believe this would be the coordinates of A. Okay, moving on to number 5, we're supposed to find the area of the shaded region. So what we're going to do is find the area of the rectangle, and we're going to find the area of the triangle, and we'll end up subtracting. So the area of the rectangle is just going to be base times height, so 17 times 10, or 170. The area of the triangle, the base of the triangle is also 17. The height of the triangle would be the same as the height of the rectangle, or 10. So we have to do 1/2 times the base times the height. Or we could do 1/2 of 170, which comes to 85. Now I've got to take the area of the rectangle and subtract the area of the triangle, and it ends up being the same. 85 units squared will be the shaded area. Okay, in the next section, this is exploring perimeter and area, and it gives you a good concept of the relationship between the two. So the first thing says, use graph paper to draw 3 non-congruent rectangles with area of 12 units. So I'm going to start my first one that has a width of 1 and a length of 12, and draw that. Here's my first rectangle. My second rectangle, I'm going to make a width of 2, and it would have a length of 6. 1, 2, 3, 4, 5, 6. And it would fit in here. So the first one is 1 by 12. The second one is 2 by 6. And my third rectangle, I'm going to do a width of 3 and a length of 2, 3, 4, and a length of 4. And now I'm going to fill in the information. So in the first one, it's 12 by 1. So the perimeter, again, our perimeter, we got to go 2 times the length plus 2 times the width. So that would be 24 plus 2, or 26. For the next one, the perimeter, actually the length is 6, the width is 2. So the perimeter would be 12 plus 4, or 16. And the third one, the length is 4, the width is 3. It's going to be 8 plus 6, or 14. And if you notice what's happening, as the figures start to look more and more like a square, the perimeter is getting smaller. The largest perimeter is the one that looks the least like a square, the very long and thin one. Okay, let's go on. Now they want us to draw 4 different rectangles with perimeter being 16 units. So if the perimeter is 16 units, one that I can draw is a 4 by 4 rectangle, which is actually the square. The width is 4, the length is 4, and the perimeter would be 16. So I want my perimeter to always be 16. So the next one I'm going to draw is going to be 6, 1, 2, 3, 4, 5, 6 by 2. So 6 and 6 is 12, 13, 14, 15, 16. This will have a perimeter of 16. The next one I'm going to draw is going to be a length of 5 and a width of 3. So that would be 5 and 5 is 10 plus 6. Again, it will be 16. 5 by 3. And the last one I'm going to draw will be, let's do a length of 7 and a width of 1. 1 by 7. So that will be 14, that will have a perimeter of 16. And let's write down what I've got. I'm going to start with the one with the longest length. Length is 7, width is 1, area is 7. The next longest length has a length of 6, width of 2, area of 12. The next one, length of 5, width of 3, area of 15, and then my 4 by 4 area of 16. So the one with the biggest area will be the one, again, that looks most like a square. That will give me the biggest area. In the example before, the one that looks most like a square gave me my smallest perimeter. And the one that looks most like a square will give me my biggest area. Okay. So going on to the next page, oops, just lost. Going on to the next page, I want to answer number 3. What type of rectangle has the largest area for any given perimeter? Largest area will be the one that is most like a square, or a square. And what type has the smallest area for any given perimeter? When it's width, assuming the side lengths are whole numbers, when the width is 1, when the width is 1, that will give me the smallest area. Number 4, does the area of a figure depend on its perimeter? Does the perimeter of a figure depend on its area? In other words, if I gave you an area of a figure, and that's exactly what happened in number 1, we were given that the area is 12, does that determine what the perimeter is? Well, no. Area does not depend on the perimeter, because when we were given that the area was 12, there were several different rectangles we could draw that had different perimeters. And likewise, the perimeter does not depend on the area. I'm not going to write it all. Because when we were given that the perimeter is going to be 16, we were able to make 4 different rectangles having different areas. Number 5, what is the difference between 100 centimeters and 100 centimeters squared? Well, 100 centimeters is a length. how long something is, or or a distance. 100 centimeters squared, I'm going to draw it like this. If each of these were 10, then we would end up with 100 different squares inside of that. That's 100 centimeters squared. So that is an area, covers this whole surface, and the first one is just a length, which is what we use for perimeter. Okay, the challenge. Recall that U means the union of two sets. All of the number in both sets put together, counting each number exactly once. For example, let's let X be the set of prime numbers from 1 to 10. So 1 is not prime, 2 would be the first prime, then 3, then 5, then 7, 8, 9, and 10 are not prime. And let Y be the set of odd numbers from 1 to 10. So that would give me 1, 3, 5, 7, and 9. And it's asking us to find X union Y. So the union of the two sets together would be every number that's in both without repeating them. So that would equal 1, 2, 3, 5, 7, and 9. That would be the union of these two sets. Now suppose figure A and figure B are overlapping polygons. So say figure A looked like this, and figure B something like this, and they're overlapping. Describe a method for finding A union B. So we could find the area of A, and we could find the area of B, and add them together, but we would end up having to subtract out the area where they're overlapping. So it's asking us, and I could write that as the area of A plus the area of B, but then minus this section, which I'll just call C, minus C. So using their notation for number 2, write a formula for finding the area of A union B. Hint, the intersection of A and B is written as A with the symbol upside down, that is intersecting B. So what I have to do is go the area of A plus the area of B, and then when I'm subtracting the area of C, what I did in the example up above, now this time, if I'm writing it in this notation, A union B would be the area of A plus B, then subtracting out A intersecting B. Okay, on to the next section. Find the area of the figure formed by 4 things happening. By the y-axis, so that's going to be one side of my figure, the x-axis, the lines x equals 4, so I'm going to go to x equals 4, 1, 2, 3, 4, and draw a vertical line, and y equals 5, 1, 2, 3, 4, 5, and a horizontal line. So the area they want is inside of this box, this rectangle. And one side of it is 5, another one is 4. The area is just 4 times 5, which equals 20 units squared. And then to recap this last thing, write the word or phrase that correctly completes each statement. A polygonal region consists of a polygon and its interior. If two polygonal regions are congruent, their areas are equal. The area of a triangle is measured, should be a D there, in square units. In fact, the area of any figure is measured in square units. Okay, that's the end of this packet for 5.1a, and you can go ahead and do the problems for this section.